In this lesson, we're going to examine the rule of sum, another counting technique. This idea applies when there are actions that cannot occur at the same time. The idea of mutually exclusive events. You roll the dice, you get a 2 or a 3. There's nothing that's both, right? Even or odd. Okay? The key word there was the word or. We come across the word or, we're going to have to add up each of the different ways these things can happen. So jump into an example here. At an international conference, either 8 or 9 countries may attend. How many different arrangements could the country's flags be flown? Well, it depends. It depends on if there's 8 countries or 9. Because if there's 8 countries, and I put all those flags up there and put them all in a row and all in a line, there's 8 factorial. But if there's 9 countries, there's 9 factorial. And because these things, it's either one or the other, we're going to have to add them together. The good news is our calculus can handle this. 8 factorial plus 9 factorial comes out to 403,200. Okay, so the word and means multiply. The word or means add. Let's look at the next one. We're going to do most of the examples today, okay? Robert works in an ice cream store during the summer. How many 2 or 3 scoop cones, using different flavors, can Robert create if he has chocolate, mint, vanilla, strawberry, and maple walnut ice cream available? So the question we have to ask ourselves is he making 2 scoops or 3 scoops? Because if he's making 2 scoop cones, he has 1, 2, 3, 4, 5 choices of ice cream, and he's got to put them in 2 scoops. Okay, so 5p2. Or if he's using 3 scoops, he's got 5 choices, p3. If I add those two things together, I've got a total of 80, I believe. Took that in there. Different scoops of ice cream that we can make. Yeah, try the next one. Sailing ships used to send messages with signal flags from their mast. How many different signals are possible as a set of 4 if a minimum of 2 flags must be used? So here's our key this time. There's a minimum of 2. It doesn't say we have to use 2. There's only a minimum of 2. So 2 or 3 or 4 flags, because we have up to 4 flags in this question. So if they have 2 flags, how many ways can they pick from their 4? Oh, there's 4 of them, and I need to pick 2 of them. Or there's 4 of them, and I need to pick 3 of them. Or 4 of them, I need to pick all 4. Okay, so we can do this in stages if we want to. We got 12 here, 4 here, 1 there. Sorry, wrong button. We have 4, 24, or 24. I was wondering why my number didn't seem right. Okay, add them all together, we get a total of 60 different combinations. That's a lot of combinations. All right. If there's a possibility of overlap, the idea that we talked about last unit, Venn diagrams, we have to go back to the idea of I got to take care of that overlap. I have to figure out the number of ways the first thing can happen and the second thing can happen and subtract any overlap. I don't want to count things twice. Okay, so we're looking at people playing cards. They have a deck of cards. Remember there's 52 cards in a deck. So there's 4 people and each are given 1 card. How many ways could they all be spades? Well, how many spades are there in a deck? It's a quarter of the cards, right? In other words, there's 13 different spades. 13 spades. And I need to deal out 4 cards because there's 4 people and they each get 1. So in other words, I need to do 13 P4. Each person is going to get a different card. There's no repetition. Once the card's out, it's gone. And I can tell them apart. I can tell who got each card. So that's 17,160. What about tens? How many ways can you give out tens? Well, there's 4 tens in a deck. I need to give out 4 cards. So 4 P4. In other words, there's 24 of them. How about spades or tens? Oh, here's where that overlap comes in. Because there's some spades that are tens. So if I do spades or tens, I'm going to have to do the spades, 13p4, plus the tens, 4p4, minus the ones that are spades and tens. Well, is it possible to give out 4 cards that are spades and tens? No. There's only one of them. Right? I can't do 1p4. That's not possible. This calculation is impossible. That can't be done. This is 0. So there's no way that I have to worry about the overlap for 4 cards. If I was just doing a single card, then I have a different problem. Okay, so 17,184. Okay, try the last one here, letter D. What about things that are spades or non-face cards? So I've got spades, 13p4. Non-face cards. How many non-face cards are there? Well, there's 12 face cards. That means there's 40 non-face cards. I'm going to deal with 4 of those. How about things that are non-face cards that are spades? How many of those are there? Well, there's 10. And since there's this overlap of non-face cards that are spades, this time I will have to deal with it. This is a possible calculation. Okay, type that into our calculators, and hopefully you guys get 2,205,480. Okay. Notice that to deal with the 4 cards, I can't have a bigger number second. I always have to have the bigger number first. So in C, it was an impossible situation. Didn't have to worry about it. But in D, where there was an overlap, it was possible to have non-face spades. There's 10 of those, right? Ace all the way up to 10. I have to worry about that. Okay, we're going to continue on with our counting methods here. Sometimes, we've actually done this already once or twice, it's hard to count the things you do want. In these situations, we want to use an idea of indirect. The idea of indirect is using the complement idea. So we did an example yesterday where we had somebody in their books for classes. We said, well, French and English have to be together or not together. Well, those two things are complementary events. The fancy name for that is indirect counting. If you take your total outcomes and you subtract the things you don't want, you're left with the things you do want. Okay, we also did an example yesterday about 4-digit numbers that are even or 4-digit numbers that are odd. Well, those are complements. So if I have my total, get rid of what I don't want, I'm left with what I do want. We're going to look at a couple of examples where those come into play. So in how many ways can the 6 members of the SAC executive present their speeches at the assemblies if there are no restrictions? Well, no restrictions means any of those 6 people can go in whatever order they want to. They can't repeat. They all have to go, and order matters. So 6 factorial. No restrictions also means the total possible combinations. But what happens if the president and vice president speak after each other? Well, that's a restriction now. If I take those 2 people, the Prez and the VP, and I connect them together and say, hey, you're a group, we're left with 4 other individuals. In other words, I've got 5 things to arrange. And the president and vice president, we don't know what order they speak in. We just know they speak one after each other. So I have to multiply that by 2 factorial. 5 factorial times 2 factorial makes 240. Part C, what happens if they will not speak one after each other? Well, that's an easy question now. Total minus together equals not. There's our indirect method coming into play. If I subtract that, I get 480. And that's way faster than trying to figure out, okay, I have my 5 people, and I'm going to make sure my 6 people are straight, and I'm going to make sure the VP and the president are not one after each other. I'm going to split them up. That's kind of complicated to figure out. This indirect method, this complement, is way faster. Okay, last question. I want to give you guys a chance to practice some stuff in this lesson. So we're making 3-digit numbers using the digits 0 to 5. Repetition is not allowed. So what can we do here? I need a 3-digit number. Now here's a trick to this question. If I make the number 012, is that really a 3-digit number, or is that just the number 12, a 2-digit number? I think that's a 2-digit number. So in other words, I don't think I can put the number 0 at the front. I can put anything I want except the number 0. So I've got the choices of 1, 2, 3, 4, 5. I've got 5 choices here. And once I use up one of those numbers, any number from 1 to 5, it's gone. Well, then I've got 5 choices left for the last 2 spots. So I'm going to have to do 5 choices times 5p2. Yeah, it's a bit of a tricky one there because you can't have the first number being 0 if you're making a 3-digit number. So I put the letter A over here. 5p2, 5 times 4 is 20, that's 100. What about repetitions not allowed and the 3-digit number is odd? Okay, well now I've got conditions again. I can't use the number 0 at the beginning, and this has to be an odd thing at the end. So what do I have to fill in first here? Well, I'm going to fill in the odd digits. How many things are odd? The numbers 1, 3, and 5. So there are 3 choices. And if I can't use the number 0 at the beginning, and I've already used an odd number up, well then I have 4 choices over here. And if I used up an odd digit at the end and a digit at the beginning, I've used up 2 digits, I've got 4 choices left over for the middle. I'm back to basic counting in this question because of these conditions. You get 48 here. Letter C, repetition is not allowed and the 3-digit number is even. Oh, I like even. Even's the opposite to odd. That's a complement. So if I want even things, I can get rid of my odd. I'll be left with even. That's a pretty quick calculation. I know my total is 100. My odd is 48. There must be 52 even. Now you don't just show me the math per se for the last question, as long as you understand the idea that indirect methods are a really good use of counting if you know things are complements. Okay, we got some more questions we're going to try. Give you some to try again today. This takes practice. Each question is different. You need to try some. The more you do, the easier it'll get because you'll get the hang of how these things work. But if you're stuck, come see me and we can go over some of them.